So welcome to the Soils Lab being online. Hopefully everybody can access everything on Moodle okay. I realize this isn't ideal, but with having to have the Tuesday labs be remote, then just to keep it fair, because they wouldn't have the hands-on activities, Friday labs are going to be remote too. You're all going to use the same video of me. And first, this is going to be a video on the PowerPoint that we would have shown first and the few talking points. And then I'm going to stop it, go get set up in lab, and then record myself doing the lab from there. So you'll want to have, let me show you the Moodle page. So you'll want to have open while we're looking through this. The PowerPoint slide PDF if you want to make notes, otherwise you'll see them on this screen as I go through them. This PDF is kind of typically how we set up all the labs, with the first, like the reading part with the background and discussion. So it has a lot of helpful, I know it's going to be backwards on yours, but it walks you through what you would have done in lab, which wasn't too much. It was mostly weighing soils, packing it into a crucible so that we could measure bulk density. And then also, talking about soil tilth, which is like typically a soil you would find outside that maybe had, some sort of mechanical process put on it, like tilling, that had been watered. So it's a mixture of looking at the bulk density of a soil that could be compacted, so we can really pack it into the crucible, or a soil that's been wet up, that's allowed to aggregate a little bit, has a little bit more pore spaces in it, so a little bit more of what you naturally find happening outside, and then comparing the two, as well as compacting them. And then also especially looking at two different types of soil, one that's a little bit more coarse textured and one that's a little bit more fine textured. So again, you'll also see this folder right here that is labeled Lab Report 5, and it contains two files that are exactly the same. It's just whether or not you prefer to type into a Word document or download the PDF, which I created as a form so that there's spaces for you to type in and it doesn't mess up the format of the document. So either one works. It really is up to you, but you need to download it, type in your answers, save it, and then you can submit your lab here when it's complete. The only thing I will make sure to mention right now is that on your lab report, there is a spot where we are going to be oven drying the soil after we wet it up. And so that takes a couple of days for all of the moisture to leave the soil. So these shaded out boxes here, you're not going to be able to fill those in today. But again, on Moodle, I'll come back here and post the final weights of these soils so that you can eventually fill in the rest of this report. And so that will definitely be up by the end of the week, and hopefully I could do it Thursday, but it might not be till Friday. But nonetheless, you'll have everything you need to complete it before Tuesday of next week, which is when this lab is due. And the other thing is that next week is our midterm lab exam. And so I'm in the process of creating a review file for that. And that will be posted up here so that you can start studying for that this week and next until your lab. So you'll meet like normal for lab next week, as long as everything's fine here. And you'll take that test in person during your normal lab times. It'll be a printed sheet that you're going to go through and answer questions. There could be other things there that you have to look at There could be some soils that you have to do the texture by feel. There's going to be a lot of like provided numbers, like calculations that have, or numbers that have already been figured out by like using the hydrometer or something like that. And then you need to use the calculations we've talked about through all the labs to determine soil texture. Definitely will be a soil textural triangle, and you'll be given provided numbers from that, and then you'll need to tell me what textural class that soil fits into. So again, by the end of tomorrow, I'll have that review sheet up so that you guys can start reviewing for that midterm. So that is everything on Moodle. And again, this is the PowerPoint that is up there for you to look through. So this lab is going to be focused on bulk density, particle density, pore space, and internal surface area. But to start out, especially since I've been working on the review, now with everything we've done in the past labs, you know how to measure soil texture both by feel and by suspension with using the hydrometers like you did last week in lab. And also because of the time limit, you know, if you had been able to leave the soil in the water in that graduated cylinder and really allowed things to settle out, it would eventually look like this image here, which I just thought some of you might find pretty cool. But again, to really get to this point, I think was after 7 hours, and we obviously don't have lab for that long. But you can see how the coarse sand settles out first, and then it's the fine sand, and you can kind of see the dark layer of that. The slightly lightish grayer color layer of silt, and then clay is still in suspension. So if we had been able to wait for longer, you know, you would have gotten a little bit more exact measurements of the soil texture, but still you got a really good idea of how it's done, of how it's measured, both by feel and by suspension with the hydrometer. But moving on to other characteristics that are related to particle size. So again, these are really big things to remember, not only for our class, but also the lab. And, you know, knowing the difference between sand, silt, and clay as far as size and the diameter range, which is listed out here on that image. Also, you know, recognizing that a lot of the times we make assumptions that the soil particles are round, and that makes it easy for using a lot of the calculations we have. But in reality, you know, sand might be round or close to round, and clay is typically a little bit more like platey or more linear, not quite round, but we still treat it as round so that we can use these calculations. So again, a lot of things that we've talked about in the past, that sand feels gritty between our fingers, typically visible to our eyes, rounded, might be a little bit angular, but it is the largest particle and it has very low specific surface area, and it doesn't hold on to water or nutrients. Silt is similar to sand in shape and composition, but we can't really see it with our eyes, and it feels smooth and silky like flour. It holds water, and it can release plant nutrients by weathering. And then clay is shaped like tiny flakes or flat platelets, has a very large specific surface area, has a tremendous capacity to hold water and nutrients, and when it's wet, clay is sticky and can be easily molded, and it is what gives part to some of the characteristics of soils with high clay contents like the shrink swell, so that's important too. But we're going to talk about surface area first. I think this goes in order in my slides. So surface area first, and then bulk density, and then particle density and pore space. And again, you'll see how these terms are really related, and it's not necessarily going in order of your report, so just be aware of that. because your report starts with bulk density and then it goes into pore space, particle density, and then surface area. But it is really important to know how to calculate the surface area and be able to understand those numbers you get from it. Because again, this is from your textbook, but this is an image of, say that big large square there is a piece of gravel. So it takes up this whole volume of area they're looking at, the 8 by 8 by 8 millimeter. So it's just one particle. It does have surface area, but it only has those, 6 sides to it of this area. And again, we're pretending it's square. So it's only got 6 sides, and so it does have that surface area there. But if you compared that to the same volume or mass of clay particles, so clay particles or even sand, anything smaller than gravel really, you're going to have more particles in that volume, and each one of those particles is going to have those, again, pretending that they're square, 6 sides to measure the surface area of. And so now going from one piece of gravel to these many pieces of sand, say we have, I don't know, probably like 10 times the amount of surface area now compared to that single piece of gravel. And a lot of things, and you can read about it in your lab report, but there's a lot of important things that deal with surface area. The more particles you have, especially like clay and silt, that can provide nutrients, the better plants you're going to grow. It's going to relate to aeration, it's going to relate to water holding and soil strength, a lot of important things that we need to think about for soils. And again, this is out of your textbook too. I just typed it into my own table, but kind of comparing sand, silt, and clay. And so again, remembering that sand would have the lowest surface area, silt would be in the middle, and then clay would have the highest surface area. You can see some differences in the behaviors of the soils as far as aeration, the ability to drain water or the ability to hold water, erosion issues, ability to store plant nutrients. So it really goes to show that having all 3 of these particles is important. And then especially in some specific ranges, clay is important for plant nutrients, holding on to water, but we get too much clay in our soil, and then we have to start dealing with the poor aeration, with the shrink swell potential, with the compactability potential being high. So something to consider when you're answering these questions and going through this. But we are going to talk about bulk density and particle density, both of these making up soil density. And these are important characteristics to know, just as much as soil texture, because the bulk density is the mass of soil per volume, and it includes both the solid particles and the pore space. So things that we can learn from bulk density are, where's our soil at as far as the amount of aeration, our water holding, how much pore space is there? Is our soil compacted? Is that why we're having issues with growing plants? Or, is this at the right bulk density to build a house on? So bulk density can be very, very helpful. And there's also slides that really compare, because there's a wide range of bulk densities, but typically, like, the lower the bulk density, the better it is for plant growth, because plants can then they have lots of pore spaces, lots of areas that the roots can easily move into, and then also have air and water available. And so as a soil gets more compacted, the bulk density then increases. So we can also tell if a soil has been severely compacted by the bulk density number as well. After we talk about bulk density, we'll move into particle density, but that is looking at the amount or the mass of soil solids in a volume and only looking at the solids. But again, we'll talk about that in a little bit. So bulk density really takes a look at just dry soil. And even though it's dry, there's still pores there that would have been full of water. So, you know, it still is considering the pore space and the solids. It's just not, it's not exactly showing like of the pore spaces, which ones are water and which ones are air. It's really just comparing the pore space to the solid space. It is really easy to measure. Really all you need is some sort of container that you know the volume of. So a lot of times metal cores are used, as you can see here in these images, and it's better to be able to take these metal cores right out to the field and be able to pound them into the ground like they're showing here, because then that core that you pull out should have a sample that's pretty close to what the plants are experiencing in the field. And I just say that because I used to have to measure bulk density all the time, but of greenhouse substrates. And it's really hard to, you know, like try to press a core into like peat, and when you pull it out, have it be really representative of what's actually happening, because peat is very, very easily compacted, or it smushes down, or you have these really long particles that makes it easy, or it makes it really hard to push a core through it. So there's this whole method of putting lots of cores together, putting a ton of like peat in it and tapping it gently, and then taking like the middle core out, and that would be packed at about the same relative density as like plants growing in the greenhouse. But anyways, I'm not trying to get off topic, but I'm just trying to show you it's really easy to do for soils in the field. You have your metal core that you know the volume of, which you are going to have to determine the volume of a core for your lab report. And so I give you that equation, and then I also give you the numbers or the information for that so that you can determine the volume. But if this is something that you do over and over and over again, you know, using the same core, then it's the same volume every time. You put a wood block over it so that you can use your mallet to tap it into the ground. And then most times pulling it up, there's not too much issue with the soil falling out, unless it's like super, super sandy. Then you might have issues with lifting that core out and it still just falls through. In that particular case, it might require a little bit more steps involved, but just think about pounding this core into the ground, being able to pull it right back up, and that soil that's in the core is, you know, hasn't been compacted any more than what it already was by this method, so it's very representative of what's occurring in the field. And again, like I said, you do need to have dry soil though, so if this field isn't very dry, or you definitely need to get rid of all of the moisture, then you typically weigh this, put it in an oven, and it tells you like why we do that and how we do it in your lab report. Wait a couple of days, and then again weigh it, and you'll be able to get the weight of the soil. And you have to know the weight of the metal core too, so that's something to always know right at the beginning too. So like I said, there's a wide range of bulk densities out there, and anywhere from 0.1 to 2.7 grams per cubic centimeter. And again, those bulk density numbers can tell you important information. And this tells you how to calculate it. I'm not really going to go through that because you can look at this yourself and also read about it in your lab report. And to make it really simple, I like to just use this equation here, where bulk density is the weight of the dry soil in grams divided by the volume of the dry soil, or the size of that core, in cubic centimeters. And again, I don't want you to get confused, but you'll see it both ways, either as the cm with a 3 show cubic centimeters, or as cc, which also means cubic centimeters. So the unit of bulk density is grams per cubic centimeter. As far as things that can affect bulk density, we talked about compaction, which is really a big one, but also the different soil textures can affect the bulk density, depth in the soil profile, and then these different management practices, which again, they talk about in your textbook, so I'm just going to briefly cover. But as far as soil texture goes, fine textured soils generally have a lower bulk density. So like your clay and your silt is typically lower than your sandy soils. But when you start to get into like the loams, makes it a little bit harder to really, if someone was like, well, I have a bulk density of 1.5, you couldn't tell them exactly how much clay, silt, and sand they have in them. But knowing where these typically range would tell you if it's like an ideal soil as far as pore space goes, or if it's been compacted. And then for the depth in the soil profile, so the deeper the soil profile, the deeper down you go, bulk densities are generally higher. And again, that just deals with the fact that typically down lower in the profile, it's compacted and you have lower organic matter. And that is because organic matter has the lowest edge of the bulk density range. So you can see like histosols or peat here, they're at a 0.1. So, things that are like 100% organic matter, they have a very, very low bulk density. But knowing that means that if you had a peat that somehow you got up to like a 0.7 bulk density, then that might be compacted. On uncultivated loamy A horizons, getting up there towards 1. And then your clay and silt loams at about let's see, I don't know. If you look down here, you can kind of see it listed on the table too, but I don't know, they're typically around like 1.3. This shows them at being less than 1.4 or 1.1. Sandy soils are typically less than 1.6. So we're heading up towards a compacted area. So again, if you knew that your soil was like, say, a silt loam that's typically less than 1.4, but you measured your bulk density and it's at 1.6 or greater, then that would be considered compacted, and you're going to start to have issues with the roots if you're growing plants there, because it's going to be very hard for them to grow through, and they're also going to have to deal with the compacted soil and less air. And then you can see on the far end of the bulk density range, we have concrete, which obviously we typically do not want for soils for several of the uses of them, but then it would be different for, building on soil, putting a building on it. But just really important to note that as you're increasing in bulk density up here to the 2s and the 2.5, that means that we're getting more solids, so more particles in a certain volume, and the pore space is really going down. And so we talked about the ideal soil. So remember, keep that in your head, that there's an ideal balance between soil solids and pore space. And so as we start to change that and unbalance it, typically not good for the plants. And like I said, your textbook talks about this, but it's just kind of cool to briefly talk about that management practices have a huge effect on bulk density. Again, not only because compaction plays a part of it, like even on forest lands, because you have equipment driving over the soil around the trees that compacts about 20 to 40% of the soil. And also you have timber harvests, so things that are leaving, not as much organic matter, that can play a role. All of our urban soils, so that's like soils along our roads and our streets, again, they are often severely compacted because of the equipment that had to drive over them to create the streets or the sidewalks. And even though we always try to plant trees along streets to look very pretty, we're basically asking them to grow in like the worst conditions ever. Your textbook talks about green roofs a little bit, so if you're interested in that, you can see how, especially with using something that might not have a whole lot of soil particles in it, that we can specifically design a media to be at a specific bulk density, and so that there's not as much like mass or weight of soil on there, and we still have a good depth for the roots to grow. And then the last one is agricultural land. So again, of course, you have equipment driving over it that compacts it, but we also do till that temporarily loosens the surface soil. But again, you typically see a long-term increase of bulk density over time as the organic matter depletes and you weaken the soil structure. So with root growth, and I've been mentioning this a lot, but you have to think about a plant's, growing out in these soils, and their roots have to be able to push their way into pores that are surrounding the soil particles. And if a pore is too small, then the root needs to either push the particles aside or basically decide that it can't grow there and it grows in a different direction. So to some degree, the density can stop roots from pushing through. And this relates to soil strength, which we're not going to get into too much. But obviously for growing plants, the soil strength needs to be at a range that still allows roots to push through. But if we were going to be putting a building on soil, then having high soil strength would obviously be very helpful. So again, bulk density is directly related to soil strength and root growth then. And it is a little bit more than just bulk density. You also have soil water content. So the water content and bulk density both affect soil strength. It increases when bulk density increases from compaction or when finer textured soils dry out. We talked about the soil texture, and then we also talked about land use and management. So then the next term, an area we're going to look at is particle density. It's another really important characteristic to know, but it is different than bulk density. So again, particle density is looking at the mass per unit volume of only the soil solids. So if you thought about like that core that they pounded into the ground to collect a sample, and that's what we use for bulk density. We were looking at everything that was within that core for bulk density, both the particles and the air spaces. Particle density basically shrinks that down and only looks at how much solid, makes up that volume. So a very basic equation for particle density is the weight of dry soil in grams divided by the volume of the soil solids. So again, only the soil solids, and that's still in cubic centimeters. They've actually gone around and measured the particle density of like many different soils out there and basically found that most mineral soils range between 2.6 and 2.75. grams per cubic centimeter. So most of the time we assume that the soil has a particle density of 2.65. Now you could actually measure this, and it's not something I was going to have you do in lab, but you really could measure it if you wanted to, and it would be kind of along the lines of, you know, having two beakers, one with a known volume of soil and one with a known volume of water, adding the soil to the water, and then like the amount displaced would be the volume of the pore space. And so you could like do the volume of the soil minus the volume of the water displaced, and that would tell you how much volume of solids you have. So you could figure it out, but we are going to, again, go off of this assumption that particle density is 2.65, except for the numbers that I provided on your lab sheet. When you are trying to figure out percent solid space, which we'll talk about, and percent pore space, then I provided both the bulk density number and the particle density number, and you'll see it ranges between 2.6 and 2.75. So it's still an important characteristic because the chemical composition and crystal structure of a mineral determines its particle density. Again, it can tell us how much pore space, you know, was originally in that sample by taking out the solid space, and you know, it's just a handy thing to know. And like I said, by knowing both bulk density and particle density, then you can determine some of these other things like pore space. So pore space is the total volume of space in a given soil, or in a given volume of soil that's occupied by air and or water. So pore space is just this area that we're calling, you know, between the particles. And right now we're not defining on whether those pore spaces are for water or for air. Right now it's just either it's a solid particle or it's a pore space. So if both bulk density and particle density are known, the total porosity or the total pore space can be calculated with this equation here. 1 minus bulk density divided by particle density, and then times it by 100 to get to a percent. And so you can then use that to determine if you have a soil that's going to be good for growing plants on. So hopefully you remember, we've hit on this a couple of times, that the ideal soil for plant growth is 50% solid and 50% pore space. And you can divide that out even further. So like the pore space is then divided into either holding water or air, and the solids are made up of minerals and organic matter. But I want you to keep in mind, you know, the 50-50 solids to pore space when you're looking at the measurements of, you know, solids and pore space, and is the soil going to be ideal for growing plants in, or is it compacted? Right, going off of this would help you answer that question. When you are trying to determine if the pores are going to hold water or air, it's really based on the size of the pore. So really large pores are called macropores, and these allow for the movement of air. They allow for quick drainage of water. So typically these macropores are going to be the spaces for air, and they easily allow plant roots to grow through and allow tiny animals like worms. So these are, the larger the pore, it's going to be airspace. So it's very common in sandy soils to have macropores. Then for water, those typically fill what we call the micropores. And these are the smaller ones that are too small for much air movement, and they're small enough between particles that it can really hold on to water, and then that can be exchanged with plant roots. So these micropores are typically filled with water. Water movement is slow, and it's very characteristic of fine textured soils that have a good amount of clay. So you can kind of consider this nice hand drawing, but you still get the idea that the larger pore spaces allow for quick drainage of water, and then they become full with air, easy for roots to grow through, whereas the smaller areas, they would actually hold on to the water then and exchange it with the plant. So we will eventually talk about soil water, but I think that's a little bit later on in the semester when we talk about like hydrology. But again, it's something important to think about along with texture, porosity, and bulk density. And the water is really important for plant growth, and it also is where the nutrients are for plant uptake. So soil water is very important. And that is the end of the PowerPoint slide. So again, that is up there for you to go through at your own pace. You have this video to watch as many times as you would like. And I am now going to go get set up in the lab to record what you would have been doing, and to give you, the numbers to fill in for your lab report. And then you're going to have to use a lot of the calculations that are provided to go through the rest of this. So if you have any questions, feel free to reach out to me or your lab instructor about any of this, but I will see you in the next video.